based on the work that we did yesterday, one of the areas that we definitely want to take a look at is factoring quadratics. And we need a refresher on how we factor quadratics. And yet in this problem, I'm not having you factor a quadratic. But this method that we're actually going to be taking a look at here is very, very closely related to factoring quadratics. In fact, they're basically just the same process, just one goes forward, the other goes backwards. All right, so in order to actually expand this, what we're doing is we're using distributive property. And of course, you know, distributive property means we have to multiply whatever's out front into the parentheses. But since that's a parentheses in itself, that means both of these end up going to both of those. In other words, everything in the first parentheses is going to multiply by everything in the second parentheses. And so anytime you see a setup like this, even way more complicated ones, you're going to be able to do it this way. And so let's walk through and see how that actually looks. First thing I do is I do the x times the x. Well, x times x is x squared. Now every now and then we get a little rusty. Is it 2x or is it x squared? Remember that squaring something means to multiply it by itself. And if you remember that, then it's a lot easier to remember. So x times itself then would be x squared. All right. Now I need to do that same x, but this times the minus 4. All right. That would just give us minus 4x. Now I've multiplied everything through by that first x. Now I go to the minus 7. So I'm going to do minus 7 times the x there. That's going to give me minus 7x. And finally, the minus 7 times the minus 4. Basically here we're multiplying a negative by a negative. And a negative times a negative is always a positive. So it's going to be a positive 28. The 7 times the 4 there. That takes care of the expanding. But of course it's expand and simplify. Do you see the simplifying we can do already? Yeah, notice we got combining like terms we can do, because both of these terms here have x's in them. And remember, in order for us to be able to combine like terms, they have to have the same variables with the same exponents, which is why I can't combine it with the x squared, because it has a different exponent. But I can combine those two. So the x squared, it stays the same. And I combine the minus 4x minus the 7x. Well, if I start with negative 4, and I go down 7 from there, I end up at a negative 11. Now, when combining like terms, they have to be like terms. They have to be the same, because it stays the same. It's a great rule of mathematics. If two things have to be the same in order to do whatever we're doing, they're going to stay the same after you do it. It's a great thing to remember, and especially useful with combining like terms. And then the 28, well, we didn't do anything to that, so it stays at 28. And now this is totally simplified. This is done. Now I said that this was getting us ready for factoring quadratics. That's because this is a quadratic, because it has x squared in it. And to factor it means to take something that looks like that and to rewrite it to look like this. We actually started with the factored form in this problem and ended up with the expanded form. In the next problem, we're going to do that same thing backwards. But how do we do it? How can we go from that form down here to the other? Well, notice where we got those numbers from. This minus 11. What did we do to get that minus 11? Notice what numbers it comes from up in the original problem. What did I do with the minus 7 and the minus 4? We just added them. And so if we add the numbers to get the minus 11 and the 28, well, remember there, what do you do with negative 7 and negative 4 to get 28?
Multiply.
You multiply them. And so I multiply them to get that. So if I want to go backwards through this process, I take a look at these two numbers and I say what two numbers add to get me the middle number and multiply to get me the last number, and that tells me what the two numbers are in my factored form. We're going to actually see that in action here. So here's a quadratic that's already expanded out, and we're going to factor it. And so in order to be able to factor this, we are looking for what two numbers add to give us the middle number. So in this case, what two numbers add to 3, and the same two numbers that also multiply to a negative 10. And yes, many of you are going to go right to what that answer is, because the numbers are fairly straightforward in this case. But I want to show you the mental process that you actually are going through in order to see that, so that when you hit the tough ones, you can handle them. Because behind the scenes in your brain, in order to find that combination, most people are starting by figuring out, okay, these are all the factors I know for negative 10. And so you start by writing out, okay, well, what multiplies to negative 10? Well, you might have started with 1 times negative 10. And then your brain would then say, okay, now is that my combination that I'm looking for? Well, I need to see if it adds to 3, so I add them up together. And in this case, when I add them, I get negative 9. Definitely not the right solution. Maybe your brain then goes to, oh, well, then I'll make the 1 negative, and the 10 can be positive. But you notice that by doing that, we still get a 9 there. It's just that all we did was switch the sign. This is actually a useful thing to know when factoring these, that if you switch the signs on both of these numbers, it'll switch the sign on your result when you add them up together. So that allows you to actually make a lot more ground a lot more quickly. Okay, well then maybe you would then say, okay, what about negative 5 times 2? Okay, add those together. That gets me a negative 3. Close, but not quite, right? Because I want it to be a positive 3, not a negative. Well, remember what I just said? If I flip the signs of both of those numbers, so make it a positive 5 and a negative 2, then I switch the sign of their sum as well. 5 plus a negative 2 gives me the 3 that I'm looking for. And so my answer then, all of these factored forms for our quadratics start the same, parentheses, parentheses, x's at the start of each, and then you just plug your two numbers in. So like plus 5 and minus 2. And that would be your final answer. Side note here, you could also have written this as x minus 2 times x plus 5. That would be perfectly fine. That order does not matter. The only thing that does matter in this is that you make sure that the 2 is actually the one with the negative, and the 5 is the one with the positive, because we do need the signs on the numbers correct. Now this is a crash course on factoring a quadratic, because theoretically you had lots of time to study this and practice it back in Algebra 1. It takes less time to pull back an old piece of knowledge, even if we've forgotten it, than it does to create a new one. As we go forward, if I'm introducing a totally brand new topic, yes, we will do more examples on that particular type of problem. All right, so now taking a look at this, the other tough type of problem that you saw yesterday, it's a matter of really getting through a lot of different pieces to what's going on with this problem. So like the first thing that we have to see is that if I'm going to make a graph, I have to understand what type of equation I'm looking at. Well, it's got these two bars in it. What do those bars mean? Yep, it makes whatever's inside positive. We call that absolute value. So this is an absolute value function that we're looking at. And it does make everything on the inside positive. Although that has a few interesting little implications when we start doing addition or subtraction inside, which we'll be seeing over time. But for now, I want you to know why it makes the graph the way it does. Because if I were just going to graph the absolute value of x, a very basic little equation there, if I were just going to do that, well, the absolute value of 0 is 0, the absolute value of 1 is 1, and so on, you'd end up basically with a line over here. It'd look like just the same old graph as y equals x. But on the left side, things would look a little different. It would not continue down like that, because of course, remember, it makes everything positive. So it would actually mean that at negative 1, you'd go up 1 again. And it actually ends up creating this kind of a V shape when we create a graph. This is the most basic graph of just y equals the absolute value of x. That's that one right there. And so already, just by seeing those bars in the equation, I know that my graph here should be some sort of a V shape. And so now that we know that it's going to be a V-shaped graph, we need to know what this other stuff is going on in here. We got this +5 and this +2. Well, these actually follow some patterns that we're going to be using all year long. This +5, it is in with the x. In this case, it's inside the absolute value with x, but any time that number is trapped with the x in some way, be it by parentheses or absolute value bars, whatever it is, it means it is going to shift our graph in the x direction. It's going to move it either left or right. In this case, a +5 moves it left. If it were a -5, it would have moved it right. And that has absolutely nothing to do with the fact that it's absolute value. That is going to be true of every type of function that you're going to see all year long. A plus will move it left, and a minus would move it right. And I know it's left-right, again, because it's inside with the x. All right, so now that we know that the +5 is going to move this thing left, we got to deal with the +2. And if the number inside with x moves it left and right, the number outside, as you might expect, it would move it up and down, and it does. So the +2 is definitely going to move it up and down. Now with the left and right, it was kind of backwards from what you would expect. The plus went left, the minus goes right. With up and down, it happens the way you think it should. So a plus is actually going to be moving our graph up. If it were a minus, it would move it down. And so what that does is that moves the entire graph. It's taking this V that used to be here with its vertex at 0, and it's going to be moving it left 5 and up 2. So if I'm going to make this graph, I'm going to go left 5 and up 2 and plot my first point there. Because I know that from that point, I'm going to be making a V. Although, I don't want to just make it as sloppy as what I just sketched in. I want to be a little more precise about this. When we draw on the absolute value graph, it's like there's a slope here of 1. Because notice there's nothing multiplied by x. And just like a line, if there's nothing multiplied by it, the slope would be 1. And if I'm going to graph something with a slope of 1, most of us with graphing a slope, we think of rise over run, so we think of it as a fraction. So 1 as a fraction is just 1 over 1. If you prefer to think about it that way, great, it'll help you get there. What it means is that from that first point, I go over 1 and up 1 each point I plot. And because it's a V shape, I do that on both sides where I go over and up. I do not go down at all from that first point. And then once you plotted those points, you have enough precision to actually draw the line out from there. Because precision does matter with these, as you're going to be seeing. Because you're next going to be making a graph like this on your assignment. And on that assignment, you're going to have to plot a few points. You start by plotting where the vertex goes, and then you plot where does the next point go. And if you don't go over and up the same amount, your graph's not going to be in the right spot. Precision matters here.